All right, if you're watching this, you had some questions on the homework from last night. And unfortunately, since I'm not able to be in class, this is the best way of helping you guys out. So this is going to be a tutorial of the 25 problems from your homework last night. Feel free to skip around if there's only certain questions that you had struggled with and needed some further guidance. I'm going to be primarily using method 1 that we did yesterday. So that was splitting up my radical into two separate radicals using my multiplication property. And again, that's going to be splitting it up into one perfect square and then the product that would give us back to that radicand. So again, feel free to skip around if you only have certain questions, or if you're struggling, rewatch the questions over again until you understand a little bit deeper. So, to get started, this top row of problems, so 1 through 4, all of these are already perfect squares. So we should recognize the first 4 as perfect squares, meaning that a whole number multiplied by itself is my radicand. So again, the number that's underneath my radical. So for this top row, all we have to do is think, well, what number times itself would give me 64, which would be 8. 2 squared gives me 4. 13 squared gives me 169. And in this case, 16 squared is 256, because 16 times 16 is 256. Now as we work our way down, this next row of problems, all of these numbers can be split up so that it's a product with one of those numbers, one of those factors, being a perfect square. So I'm thinking, how can I split up 24 so that one of them is a perfect square? Well, 4 times 6 gives me 24, and 4 happens to be a perfect square. I know the square root of 4 is 2, so 2 times the square root of 6 is my final answer. For 48, again, I can split it up into the product of a perfect square and another number. In this case, 16 is the biggest perfect square that goes into 48. So 4 square root of 3 is my answer. For 32, again, we can split that up into 16 times something, in this case times 2. So 4 root 2. 98, a little bit trickier. Again, we want to start by going through that list of perfect squares and seeing what's the biggest number that goes into my radicand. And in this case, 49 times 2 is that best option. So because we have this coefficient on the outside, that's going to stay outside my radicand, my radical. And then again, I'm going to split it up just like I did before. Square root of 49 times the square root of 2, because 49 times 2 is 98. And now I have 5 times 7 times the square root of 2. So before I'm done, I just make sure everything that's outside of my radical gets multiplied together, and the inside of my radical is completely simplified. So here we have 35 square root of 2. Working our way down, number 9 is a little bit tricky because we would think that we should be simplifying because that's our instructions, but there's no way to split up 3 any further than it already is. The only way to get 3 is 3 times 1, and neither of those is a perfect square that helps us out at all. So this is actually already simplified. 3 root 3 is my answer. For number 10, I'm trying to split up 200, which in this case is 100 times 2. Square root of 100 is 10. So my outsides are 10 times 10 root 2, which gives me 100 times the square root of 2. Getting into my variables a little bit, this becomes more of method 2 that we did yesterday, where we were trying to find pairs of numbers, or in this case pairs of variables, that one can sacrifice themselves to save the other. For number 11, we've got y squared, so we've got one pair of y's. So one would sacrifice themselves to save the other one. So one gets saved outside of my radical, the other one has sacrificed himself, so it does not remain underneath my radical. So I end up with just y for my answer. For number 12, I've got a pair of a's, so one can sacrifice themselves to save the other. So one of my a's comes outside of my radical. The other one sacrificed itself. And this b, since it didn't have a buddy, didn't have a partner, it stays underneath my radical. For number 13, continuing with that, c to the fourth power means I have 2 pairs of c's with no leftovers. So again, one sacrificed to save the other. For d to the fifth power, I've got 2 pairs, 2 that'll sacrifice to save the other 2, but then I have one more left over since it's d to the fifth power. So 1 didn't have a partner, didn't have a buddy or a twin, so it has to stay underneath my radical. 14, we've got an even number, so there's 50 pairs of k's with no leftovers. 15 starts to get a little bit messy, but my process hasn't changed at all. I'm still just focusing on each of these different pieces and trying to figure out how many pairs I have. Well, square root of 4 is just 2, so I end up with 2 times 2 on the outside. I've got 1 pair of x's, so it'll come on the outside. 3 pairs of y's, so y to the third, with 1 y left over. And I've got 4 pairs of z's, again with 1 left over underneath my radical. So I end up with, in total, 4x y to the third, z to the fourth, times the square root of yz. Like I said, messy, but really the process is no different than what you've been used to. Same thing applies to number 16. My 40, I can split that up into square root of 4 times 10. My r to the fourth and my s to the 12th are unaffected. So I can take my y to the fourth becomes 2 on the outside. My square root of 10 remains. I've got 2 pairs of r's to join my other 2 pairs of r's. So I end up with r to the fourth with nothing left over underneath. And for my s's, I have 6 pairs that sacrifice and save evenly. So all I have left underneath my radical is that 10.